everyone, the paper we will discuss today is overview of the SPARC physics, basis towards the exploration of burning plasma regimes in high-field compact tokamaks. If you have any questions, I'd be happy to hear your comments. Section 4. Core Plasma Physics. The PRD scenario presented in the previous section represents the most stringent plasma discharge for SPARC, and therefore much effort has been developed to the understanding of the physics of the PRD and the resulting machine engineering requirements. The PRD is a scenario that leverages conventional H-mode operation to achieve performance goals. This choice does not preclude operation in other high-performance operational regimes, but extensive experience with conventional H-mode in tokamak operations makes it a conservative choice for projecting SPARC performance. Due to the lack of first principles models for the low to high confinement transition, LH power threshold, and empirical scaling law approach has been taken to project H-mode success in SPARC, as shown in Figure 2a. At 12.2 Tesla, the minimum power required to access H-mode in DT plasma is projected to be P equal 21 MW and occur near N equal 1.9 times 10 to the 20 powers per meter cube. The total auxiliary power installed in SPARC is in excess of this value, P equal 25 MW, and given the non-negligible alpha heating that may occur in L mode, it is then inferred that SPARC will likely be able to access H mode in its full field DT scenario. Access in less stringent scenario, such as 8 Tesla, are also possible and will be explored in the pre-nuclear phase of SPARC of characterized H-mode operation and extend the databases to close gap in our projections to pilot plant during the H-mode phase. The increased density will raise the power requirements, and thus it is expected that significant alpha heating will be required to sustain robust H-mode operation. SPARC will feature of gas filling system as baseline fueling actuator, but the implementation of pellet injectors will not be precluded. MHD stability analysis with the EPED model, shown in Figure 2b, indicates that SPARC will operate mostly with pedestals that are filling limits. Owing to the low normalized density and the strong shaping of the PRD scenario. The transition to the borrowing branch occurs at significantly higher density or lower elongation, and therefore a degradation of the pedestal pressure with density. Signature of borrowing limits pedestals is not expected. Pedestal performance is therefore favorable to upward exclusions in density from the PRD nominal operation. Analysis of the sensitivity of the pedestal predictions to changes in plasma parameters such as elongation, triangularity, normalized pressure, and pedestal density has been performed in reference, demonstrating that the solution is robust to expected variations in plasma parameters as presented in reference. An advanced integrated modeling approach has been utilized to predict plasma kinetic profiles and associated plasma performance. Figure 2c shows the temperature and deposited power density profiles predicted for the PRD using the Trans-SP power balance framework coupled to the TZLF SAT-1 model for turbulent transport. Pedestal pressure as given by EPED has been used as a boundary condition, and pedestal density is chosen so as to achieve an operational volume average density of N equals 3.1 times 10 to the 20 powers per cube. Predicted performance of this scenario is Q equals 9, remarkably close to the empirical predictions with popcorn analysis with the same amount of axially heating power. The TZLF gyro field turbulence model indicates that SPARC will be dominated by ion scale ion temperature gradient ITZ models with some unstable electron scale models in further or regions of the plasma. Even through the PRD scenario is mostly electron heated, radiation is the dominant heat exhaust mechanism for the electron energy channel, leading to heat flux ratios of the order of Qi per Qe. 2-3 throughout the entire plasma core. As is often the case is today's neutral beam ion NBI heated discharge. Nonetheless, SPARC will not have external torque input, no NBI, and SPARC discharges will predominantly feature moderate to low toroidal rotation. Empirical predictions of SPARC intrinsic torque and rotation have been performed, and intrinsic torque of 4 Nm is predicted, leading to a core Mach number of m 0.16. Extensive gyrokinetic analysis of the SPARC PRD scenario has been carried out in reference. Gyrofluid modeling results are confirmed with linear and nonlinear CGYRO simulations of the core of SPARC. Long wavelength ITZ has a dominant role throughout the core. Also, presence of subdominant trapped electron mode turbulence is found in outer radii. The contribution of short wavelength turbulence to the total heat fluxes is estimated to be minimal, and electromagnetic fluctuations and the inclusion of toroidal rotation at levels empirically estimated are found to have favorable effect through stabilization of the ITG turbulence. High Z core impurity accumulation has been assessed through scans of the impurity gradient scale lengths in nonlinear gyrokinetic and neoclassical transport simulations. Leveling peaking factors that do not imply dangerous accumulations up to rho equals 0.4. Future work will extend it, such as analysis, to the near-axis region and will include other operational scenarios. The possibly favorable effect of fast ions from off-axis ICRF minorities is currently being evaluated, which could lead to the attainment of the Q-2 mission, and burning plasma has a lower magnetic field and plasma current by means of improving energy confinement. SPARC net energy gain mission will be achieved with ICRF as the sole axially heating mechanism. In particular, minority heating scenarios with fast wave at 120 MHz will be used for optimal absorption and bulk ion heating at both full 12.2 Tesla and reduced 8.0 Tesla on-axis magnetic fields, and antenna a spectrum of K 15 to 18 per meter has been found to provide a balance of good edge coupling and core absorption as described in detail in reference. Methods to prevent contamination of the plasma with high Z impurities at high ICRF power operation have been taken into account during the design of SPARC antenna. These include the use of 4-strap, field-aligned antenna with low power density, following extensive experimental experience in allocator C mode and ASDEX upgrade, even through the PRD scenario requires 11.1 megawatt of ICRF power during the high-gain H-mode flat top. A total of 25 megawatt of coupled power will be available, driven by H-mode access requirements in DT. A DT 3 helium scheme is used for nominal operation in PRD with 5% 3 helium concentration in this regime. 80% of the ICRF power is dumped by the first 3 helium. Fundamental resonance as predicted by TORIC and FPPMOD. After slowing down, bulk ion species received 78% of the total ICRF coupled power. The commissioning and demonstration of SPARC ICRF system will occur with scenarios at 8.0 Tesla and 12.2 Tesla, utilizing H minority heating and 3 helium minority heating in 4 helium main ion plasma. Access to high fusion power and burning plasma regimes in SPARC will produce significant amounts of energetic alpha particles. This first alpha population, along with the hot ICRF minority ion tail, poses a potential risk of damage to the first wall and other tokamak systems if significant losses occur due to classical orbit effects and MHD instabilities. Research has focused on ripple include induced losses, as they can drive the engineering design of the toroidal field magnets and may influence the design of the limiter surfaces and plasma-facing components PFCs. Work with ASCOT and SPIRAL has ponents PFCs has shown that magnetic field ripple from perfectly aligned coils 0.15% nominal edge ripple does not cause the significant peak surface power density smaller than 250 kilowatt per meter square and a subdominant to neoclassical first orbit losses 2.8% as described in simulations with imperfectly manufactured and imperfectly positioned coils are being used during the design of an optimized wall shape, as well as the ICRF antennas and limiter locations because of their low toroidal mode number magnetic field perturbation. We expect the alpha losses associated with the effect of the error field correction coils EFCCS to be small compared to ripple-induced losses, even though the latter are already expected to be small. Future work will explore the combined effect of the toroidal field coils, misalignment, and EFCC on fast ion populations in SPARC. Thank you for listening to the end of today's show.